So here we'll have part 2 of a video about how to convert between polar and rectangular coordinates. And I'm intending this to be part 2 of a video I already made where this was the last problem that I did. Okay? Alright, so I want to do one like this. So let's look at this one here, which is styled after this one that is done in another video, but here we have a constant that's not specified. Okay, so and sometimes we have to deal with that in math and science, that we might have some equation and it has some letter, maybe a Greek letter, but that it's understood that that is a constant that's just not given at the moment. All right, but nonetheless, this number k is a constant, and I'll also tell you for this problem that k is greater than 0. Now it says convert to polar form and then sketch the graph. All right, so that's two things then. The polar form and then the graph. All right. In the last example I did, in the last video I did, then we find that the polar equation, r is 6 cosine theta, happens to be a circle that has a radius of 3 and a center at 3 and 0. Okay, that's what it is. And you might imagine if r is equal to a constant times cosine theta, then you'll get a circle with, you can extrapolate what the radius and the center would be in that case. All right, but that sort of thing in polar form will be a circle like this. Now, so here with this one, I'll do like each part separately then. First, the conversion. How can we convert that to a polar form? Okay, well, that will be the easy part of this. I've got equations that convert x squared plus y squared and x already. I discussed those in the other video like I was saying, but for example, x is convertible to between polar and rectangle as x is r cosine theta. Also, we can say that r squared is x squared plus y squared. So that'll take care of most of this. X squared plus y squared, that will be r squared minus 6k, and remember k is a constant, but x is convertible to be r cosine theta. So we'll say 6k times r cosine theta. All right. Now that is in polar form. The rectangular coordinates are gone at this point. There's the x and y aren't there anymore, and we've introduced r and theta in their place. So that's polar coordinates. Polar coordinates have r and theta. This equation's in polar form. Now from here, I can factor out the r that's common to both of those terms. And then I get like that. But from this point, I could divide both sides by r, and I'll get r minus 6k cosine theta equals 0. So my polar form will be r is equal to 6 times constant k cosine theta. All right, there's my polar form. To give the rectangular form, x squared plus y squared minus 6kx is equal to 0, gives me an equivalent polar form as r is 6 times k times cosine theta. Now, all right, that part's done. The conversion's over. What is this, though? Sometimes we need to know what things are. Is this a circle? Is it a line? Like, whatever. It might be hard to tell from this because polar coordinates are new to us, but maybe from that we can figure it out. Okay? And yes, that will be just like how we did this one. All right, I'll have to urge you, if you didn't see it, go back and look at the last problem in the video that I list before this one. But it's an equation like this will be one like that. It will be circular. We just need to complete the square to figure out what the center and the radius is. Okay? So, all right, conversion part's done. Let's look at how to think about what the graph is. Okay? All right, so let me recopy. So I'm going to do x squared minus 6kx plus y squared equals 0. I did a little bit of rearranging, but that's what I have up there. So in order to make this factorable so that it looks more like the standard equation of a circle, I said we needed to complete the square. So I need to take half of that coefficient and square it and add it to both sides. Okay? So if I do that, let's see, what's half of 6k? It's going to be 3k. And if you square it, you'll get 9k squared. So I'm introducing that on both sides. I introduced that because it now makes this factor. Okay? It makes it factor like this, x minus 3k all squared. That's how you factor. X squared minus 6kx plus 9k squared. It's going to be x minus 3k quantity squared. And then over here, plus y squared is equal to 9k squared. So now we know what that thing was. Like, what was this? In order for me to think about the graph, it's this. Okay, and then what can we say about this? Well, this is the standard equation of a circle. It will have a center point at 3k, where again, I can't tell you what that number is, but I know that k is given to be a constant. And 0. 3k for the x coordinate, 0 for the y coordinate. And it has a radius of 3k. Okay, alright, I'm gonna have to never write in pen when you do math. 3k. There we go. So, okay, think about it then. What's that going to look like? Let's do this. Let's sketch the graph real quick of a circle with those specifications. So let's see, center 3k, radius 3k. Okay, so imagine if you had some point out on the x-axis that was a distance of 3k. Then that would be a center. Okay, and then if the radius was also 3k, that would put a point right there and another point over there. Okay, all right, so let's see. What's this point? That point has a radial coordinate of 6k and 0 degrees. Okay, this point right there has a, now I'm sorry to mix things up a little bit, but it has rectangular coordinates of 3k and 0. So yes, I am mixing things up. This one's polar, and this one's rectangular, but I just wanted to put them both there for reference, okay? But there you have it. The polar equation, r is equal to 6 times k times cosine theta, k being some positive constant. Well, it looks like that because it's a circle. It has center 3k and 0 on the x-axis, and has radius 3k. It has this point on the far edge out there, 0 degrees for theta, 6k for r. All right. So one thing I didn't mention on the last one is that that point being there in polar coordinates is consistent with this equation. We haven't used the equations like this yet, but say you put 0 for the angle right there. What's cosine of 0? It's 1. And what's 1 times 6k? It's 6k. So r is 6k. So every point that's on here, even though I haven't gotten to that point in the lessons, you know, if it's on the graph, it's got to be consistent with the equation. Okay, it's got to satisfy that equation. And those numbers do. Okay? All right. So let's do this one then. Let's few more conversions. Then I think we've done enough conversions, and we can move on to something else. So convert to polar form, and then sketch the graph of y is equal to 8. Well, so that one's real easy to sketch. I don't have to do anything with it. But I thought I might mention. Let's see. Yeah, I know I did this at some point. There was this other problem where I said, what does the polar equation r is equal to 3 look like? Okay, well, in polar coordinates, there is a theta also. What happens to theta? Say I tell you, here's your equation, and it's in polar form, And I don't mention theta. That just means there's no restrictions on theta, and theta can be anything. So what's this? Like, this is in rectangular form. And rectangular coordinates have x and y. So the x is not mentioned. What does that mean about the x? It means the x can be any number. There's no restrictions on it. So where are all the points where y is 8 but x can be anything? That's a horizontal line. All right? Okay, now I know that you may have already been aware that y is equal to 8 is a horizontal line. But, you know, I can give you reasoning that's consistent with other things I've said in this lesson. Okay? If you think about all the points where the y coordinate is 8, but the x coordinate is anything, that's a horizontal line. Okay? All right, so I know what this is. The graph part won't be difficult. Let's talk about the conversion part. All right, so convert. All right, so, well, okay. We have some equations to work with, one of which is relevant for this problem. All right, so there's all my conversion equations that I ordinarily would use, and that's the one I want this time. Y is convertible to be r sine theta. So well, that's pretty simple. R sine theta, that's y. That's equal to 8. And that's reduced quite a bit already, but I can take a little bit further. I can say r is equal to 8 over sine theta. Okay. So I'll go ahead and I'll give you this for my polar form. I'll say r is equal to 8 times cosecant theta. All right, there's my polar form. It's not as simple as the rectangular form, but nonetheless, there it is. Okay. It is exactly the same thing as y is equal to 8. But there's the conversion. That's the equation. Now, you will see these as we go through and do other things with polar coordinates. You'll see equations like r is equal to a number times cosecant, or r is equal to a number times secant. Those will be horizontal and vertical lines in general. Okay. What about this one? I already told you this one is a horizontal line. So let's go ahead and talk about the graph. And I want to unify it with this equation. So y is equal to 8. Yes, it is a horizontal line that goes through 8 on the y-axis. So suppose this is my ordinary graph paper. And you can imagine what a horizontal line looks like. There it is. All right. Okay. So there is r is equal to 8 cosecant theta. Can I give you a point that's consistent with that? Like, what should this point be right there in polar coordinates? Let's do polar coordinates. What should be the polar coordinates at that point? It should be 8 for r, and it should be 90 degrees for theta. Isn't that right? If this is the same as that, and if this is a horizontal line that goes through 8 on the y-axis, then if you rotate 90 degrees, you would have to go outward a radial distance of 8 to get to that point, all right? So yes, that point should be on there. There should be a point 8 for r, 90 degrees for theta. Is that consistent with this equation, though? Let's try it out. What's say you put 90 degrees for theta. What's cosecant of theta? That's 1 over sine of theta. So that's for 90 degrees, that's 1 over sine 90. That's 1. What's 8 times 1? It's 8. So yes, those numbers come right out of this. Okay? All right, there it is. So now when you see things like that, whether that's 7 cosecant or 4 cosecant, then you'll know that it's a horizontal line. Okay? And for me doing this now, I just really have the objective of getting you to be familiar with some things that you'll see later on. All right, maybe, so that's not so bad. Let's see. Let's do 2 more. Yeah, so 2 more. Convert to rectangular form and then sketch the graph. What about that one? Do you know what the graph of that looks like? Do you just know? Probably not if you're just learning this. But maybe if we convert to rectangular form, then we'll know. So just to give you a little heads up on this, kind of give you a big picture view if I can. Let me see, I need to find something to show you. There we go. This one will be sort of like doing this one in reverse. You know, this rectangular equation is equivalent to this polar equation. It doesn't matter which one you start with, you can get from one to the other. This time I've got a polar equation, and I want to put it in rectangular form, and maybe then, because I'm used to working in rectangular coordinates, maybe it will be obvious to me what it is. Okay, so let's do the conversion first. And then hopefully we'll recognize what we have. So I get r is equal to 5 times sine theta. All right, now I guess the trouble with this one, the way that it is that none of my conversion formulas seem applicable to it. You know, I can convert, I don't know, r sine theta, and I can say that's y. But like sine theta itself doesn't convert into purely rectangular coordinates. R sine theta does convert, but sine theta doesn't. So I'll just do something to bridge the gap between what I have and what I showed you on the other page. So say I take this equation and I multiply both sides by r. Then I'll get something that I can work with a little bit easier. So let's see, multiply both sides by r, I'll get r squared. Okay, so that's good. I've got a conversion for r squared. And on the other side, I'll get 5r sine theta. And I've got a conversion for that. I can know what r sine theta is. Now, everything here is on my list, right? Everything. R sine theta, that's y. But then x squared plus y squared, that's r squared. That's the kind of thing that I wanted to get. And that one step did it. All right, that's all I had to do. So here goes. This is x squared plus y squared is equal to 5y. All right. Now, I guess we could say we converted it at that point, but still, like, we might be in the dark about the graph. Okay. So again, I'm thinking of it like this. Is there like some way to write this in a recognizable form, such as the standard equation of a circle, right? That's what it will become. I can make this right here through completing the square be reducible to that, and then I'll know all the specifics of it. That it's a circle, that it has a radius of whatever, that it has a center of whatever, and so on. So now I'll do this. I'll group the y's together. Okay, and then there's a certain number that if I add to this y, these y terms right here, will make it factorable. Okay, and we said that that number would be half of this coefficient squared. So I'll say y squared minus 5y. Half of 5 is 5 over 2. Squared is 25 over 4. So 25 over 4, that's the number that I want. Now I have to add 25 over 4 over on this side to keep it balanced. But that number, of all numbers in the world, makes this factorable. Okay? And in fact, the way that it factors is y minus 5 over 2 squared. Okay, so now we know what it is. I'm going to give this as the rectangular form. I guess like you could give this one or that one. They're equivalent, but we get more information out of this one. For example, I can tell it's a circle, right? It's the standard form of the equation of a circle. It has a radius of 5 over 2, and it has a center at 0 and 5 over 2 on the y-axis, all of which is in rectangular coordinates. Okay, so there's my conversion. That part, getting to here, makes the graph pretty easy to do, I think. All right. Okay, second part, graph. All right, so maybe something like this. I've already told you what it is. So let's do like this. Okay. How would you sketch a circle that has a center on the y-axis of 5 over 2 and has a radius 5 over 2? Well, it's going to be like this. Okay, right? Sure. Okay, so that's the graph of r is equal to 5 sine theta. Can I give any points for reference? Like this point right here. If this is the graph of a circle that has a center point of 2.5 right there and a radius of 2.5, then this point should be what? It should be 5 for r and 90 degrees for theta. Isn't that correct? Like in polar coordinates, that point should be on here. Is that consistent with this equation? It should be. I mean, if it's not, then either that point's not correct, or this equation's not correct, or our conversion was not correct, or something's not correct somewhere. So let's try it out. In this equation, if I put 90 degrees for theta, what do I get? Sine of 90 degrees is 1. And then times 5 is 5. So r is 5 if theta is 90 degrees. Well, sure, that point's right on there. Okay? All right, and it would be on there anyway if the radius was 5 over 2. That would make the diameter 5. That would make this distance from here to there 5. So it's consistent with the center and the radius being what I found them to already be. Okay. All right, so that's similar in some ways to others that we worked with. But I mean, if we'd be dealing with polar coordinates, we'll see lots of circles because normally formulas for circles in polar coordinates are simpler than they would be if you were dealing with rectangular coordinates. Okay, so get used to seeing circles, basically. Let's look at one more. Okay, this one is definitely not a circle. It says convert to rectangular form and then sketch the graph. I think I would like, I want to do this one in a different order than before. I think I'd like to do the graph part first. Okay. I mean, we just need to get it all done. I guess it doesn't matter what order you do it. You can do it whatever order you think is best. But can you tell me what this is? Like, what kind of thing is that? We're in polar coordinates. This is polar form. This is not rectangular. It has theta. It says theta is equal to 2 pi over 3. Okay? That's not quite like this one, where this equation for a circle of radius 5 over 2 and center 0, 5 over 2, it's not an equation that has both r and theta, where you plug in the theta, you do the math, and you get the r. It's not like that. R is not given. What does that mean about it then? Well, isn't that kind of like this one? Why is the graph of y equals 8 a horizontal line? Why is that true? Well, because no restrictions given on the x. So just all the points where you go up 8, but you go left and right, however you go left and right. All those points together collect to be a horizontal line. Okay, so all I'm trying to say here is that just implied in the fine print, I guess you could say, the fact that I didn't mention anything about r is it's implied that r could be any angle, or any number, sorry. Okay, so where are all the points where the angular coordinate's 2 pi over 3, but the radial coordinate can be anything? Well, those would just be points along a line. Okay, that's all they would be. And then here's, in fact, where they would be. So 2 pi over 3, so that's 120 degrees. So imagine that I had a line oriented like this. Okay. All right. That would be it. Okay. So there is theta. 2 pi over 3 in radians, or 120 degrees if you want it in degrees. So all the points on that would be here. If r is positive, it's going to be out here. Okay. And if r is negative, it's going to be out there once this angle is established. Okay. All those points are greater than 0, are less than 0. But it's just r can be anything. The angle's established. You go out radially however far you go, forwards or backwards, and they've all got to be on a perfectly straight line. Okay. All right, so this the first thing I wanted to say is it's a line. It's a line like that, in fact. Okay? All right, so there's the graph. It looks like that, and that angle is there for reference. Part 2 then. The other part says, well, can you convert it to rectangular form? Well, maybe we'll get some more information about this line. So let's see. We got theta is 2 pi over 3. My opinion on this one is I don't think any of the conversions are extremely applicable to this one. Okay? So here's what I'd like to do. Imagine that there's a point somewhere on this line. Given that it has an infinite span to it, there's a point somewhere on that line that has an x-coordinate of -1. And it's got a y-coordinate of who knows. I'll try and figure it out. But there's got to be an x-coordinate of -1 somewhere, right? Well, then I get this little triangle formed by the x and y coordinates. Tell me what this angle is. So if this angle is 120 degrees, then that one right there, between this line and the negative x-axis, that's going to be 60 degrees. Okay? So just by that assumption that there's got to be a point where the x-coordinate is -1, well, then got the angle, I can figure out the y-coordinate. All right? So here goes. We'll do something like this. We'll say tangent of 60 degrees is equal to y over 1. All right, just working in this triangle. Okay, I know that number is -1, but let's just say I work in the triangle for now. Then tangent of 60 degrees is √3. And so that means that y-coordinate has to be √3. Okay, so I'm going to go left 1, I'm going to go up √3. All right, so that's that point. There's that, for that point right there that I chose just out of convenience. Then the x-coordinate, now these are x and y coordinates. So I have to be as clear as I can to you what kind of coordinates I'm using. This is -1 for x, and it's √3 for y. All right, so there. Can you give me the equation of a line in rectangular form, rectangular coordinates, that goes through the origin, but also has this point on it? Well, it's a line, let's give the specifics, with a slope of -√3. That's the rise and the run for this thing. -√3. Okay, and y-intercept at the origin. Now again, that's x and y coordinates. Okay, so I can give you the equation for that line. Initially, I just knew it was a line. Now, for the purposes of giving you the rectangular form for the line, then I'll say this. It's y equals -x√3. There's the equation of a line with a slope of -√3, given that it has this point on it, and a y-intercept of the origin, given that it has to go through the origin based on our initial analysis of it. All right, there's that. Okay, so the graph, the conversion, that's the whole picture.